All right, this is chapter 9, problem 79. If we look here to read the problem, it's a bit of a long one. I'm going to assume you have the book with you on this one in the interest of time. Problem 79 in chapter 9, I should say. Essentially, we have an adventurer going using a mountain climbing technique, and they need to get past they need to traverse a deep chasm, and essentially we want to see if the rope that they're going to use to traverse between this chasm is going to break or not, based off of the tension in the rope. So this is very similar to two odd problems before, chapter 9, problem 75, in that you just need to do the sum of the forces. So we're looking for X here. We want to see how far it's sagging, and then based off of how far it sags, we also want to see what the tension in the rope is and if it's going to break or not, right? So let's calculate all these things. We can use the Newton's second law, and this will tell us everything we need to know. So first, of course, as we always do with forces, let's draw a free body diagram. So it's going to look something like this. And of course, we have to remember our vector signs. So 12.5 meters both ways. We have angles there at the top, the x distance. We don't know what the sag is for the person. They're obviously being affected by gravity. They have mass, and there's tension pulling them in both ways as the rope is tied onto the tree. Yes. So to include the safety factor, the tension must be less than or equal to 2,900 newtons. That is to say, that the tension must be no more than 2,900 newtons. And so we have the exact same equation from problem 75, 2 times the y component of the tension, which is just Ft, the tension force, multiplied by sine theta, subtracted by mg is equal to 0. And with that, if we have the maximum force possible there, which let's just call it 2,900 for now, then theta would be, well, you have all these numbers, right? G is 9.81, mass is 75 kilograms, and the Ft max is 2,900 newtons. You can calculate theta minimum to be 7 degrees at most. So this means we can more or less interchange sine and tangent as before because of the small angle approximation. But also, from the triangle that we see on the left side in the free body diagram, well, it could be the left or the right. Let's just say on either triangle, we can use our trigonometric brain to solve this problem. So if we say tangent theta min is equal to x min over 12.5 meters, we can calculate the distance, the minimum distance needed for there to be a sag. And as we can see, we already calculated the minimum angle needed, so we can just plug that in, multiply by 12.5, and we find that the sag is going to be 1.6 meters. That's to say the minimum distance the rope must sag based off of the maximum force is going to be 2,900, is going to be 1.6 meters. Now, taking that sag and multiplying it by a fourth, let's look at if the Tyrolean traverse is set up incorrectly so that the rope sags by only a fourth of the distance found. What's the tension? Then we want to say, okay, let's multiply 1.6 by a fourth. So it's going to be about 0.4, but let's do it exactly, and it'll be 0.3992 meters. We can use this distance to find out what the tension on the rope is by working backwards. So what we can do here, so we go to the next page. So as I said, you multiply by a fourth to get 0.3992. Use that distance to find the tension. And so essentially we flip around the tangent equation and take the arctan of both sides to cancel out the tangent on the left to get the angle. We plug in our new distance rather than 1.6. Now it will be 0.3992 meters. Then we calculate our angle. Our new angle is going to be 1.829 degrees, which we can then plug into the sine below, the sine theta equation below. And mg over 2 sine theta will give us the tension with all of our numbers plugged in should be about 12,000 newtons. More exactly, it'll be 11,512 newtons. And with this, the rope will not break, but rather than the safety factor being 10, it's only going to be 4. Because if you divide 12,000 by 4, you should get about 3,000, which is what our force is here, right? So this is about 3,000, 2,900, just 100 off. And this is 500 off, but still pretty close to 12. So a safety factor of 10 would have had a 29 kilonewton tension.